Welcome everyone. I hope you're enjoying Unite so far. I must say, if anyone who came to Berlin last year, the food is much better this year. So I'm here to talk to you guys about Universal Render Pipeline, but more specifically, how it was used in the boat attack demo that you might have seen at the keynote, and that has been in development alongside what was Lightweight Render Pipeline, now called Universal Render Pipeline. My name is McGrail, and I am a technical artist at Unity. So, here's a short overview of what I'll be talking about today. I have a short intro, just show some some old kind of footage from boat demo and where it's come from. I'll briefly go over some of the features that I've used just in Universal RP in general, like very basic kind of the quality settings, the render pipeline asset, that kind of stuff. Just briefly go over that. Then we'll dive into shader graph. I'll show you some of the shaders that were set up, from a basic one to a more complex one with custom function nodes, etc. We'll jump on to camera callbacks. These replaced kind of the old callbacks in Unity, so they're good to know and understand. And then move on to render pass features, which is kind of our nice, easy wrapper for creating extra passes or customizing the render in Universal Render Pipeline. So, the very early version of the boat demo looked quite a bit different. This wasn't any kind of like show on the actual lightweight render pipeline at the time. Obviously, it just started out at a very basic phase. But already back here, we had the ability to be able to pull off planar reflections. This had obviously changed quite a bit since it was created then, different callbacks, etc. And now this is what it will look like at Unite Berlin, which was just over a year ago, I think now. Again, quite, a lot more is in there. We've got water, we've got, the planar reflections coming in, and that kind of stuff. But we didn't have any of the render pass features and the custom renderer stuff. That wasn't really integrated into Lightweight Render Pipeline at the time. We had it back internally as we were using it in the actual forward renderer. But it wasn't exposed, and it wasn't a nice, easy, kind of clean API for users to be able to pick up on. And then this is kind of what it looks like today. Here you can see we added the day-night kind of cycle. We've got planar reflections going on still, but now they're using the new callbacks. There's some renderer features that are adding extra details into the water, which I can go on about, and a lot of heavy kind of shader graph usage, because this is kind of very nice at this point. So I'm going to dive into the demo now. Here's the link for the boat attack GitHub repo. I've got it in the actual tree, or the branch, demo work. This is the branch we've been using for Unite. So this has a lot of the more recent updates, and it is recommended if you're going to load up 19.3 to use this version. So I'll just dive over into the editor here. And first off, let's just have a look at what it plays like. Oh, was that an instant crash? Nice. Best way to start a demo. Look at that. Yeah, let's start that one again. So, some things I'll show you here is that we got it running on essentially a wide range of devices. We had it running on 6 devices live on stage at the keynote, which was actually quite terrifying for me. Never bring 6 devices live on stage to demo at once. It was definitely a kind of a heart palpitating moment. So here we have the demo. Let's see if we can play it this time, or we're going to get in an infinite crash loop. No, we're going. Okay. So I make use of Cinemachine here, by the way, and I've got this greedy camera taking all the control, so I'll just go back to the boat. So essentially, the idea of this demo was to create a vertical slice of a boat racing game. A big thing we started to do recently at Unity is the production-driven development, and this is really needed. Now he's crashed. Oh, I made it. This is it's super useful. It makes sense to build a use case and then test those features that we create at the same time, because we could go ahead and make a feature, but without trying it out in real, world scenarios, we're not going to know whether it ticks all the boxes or it can do all the things we would like it to do. So here, I've managed to make use of quite a lot of the features that are in Universal Render Pipeline. We're using shader graph. So that's used quite heavily. We use the custom renderer features, which is also the custom render path system. This was used to add caustics in the water. It was also used to add essentially there's a water effects path that creates the foam and the trails of the boats. It also helps create little foam splashes around each of the floating objects. It makes use of the burst system, so C# jobs. They're used to calculate height positions in the water. So we can figure out whether certain parts of the boat are underneath the water and apply buoyancy back on it. So it was a good mash of features, and it has been very useful every time we've done massive changes to the universal render pipeline to see if we've broken anything or if something needed some more work and polishing. So to get it running on all the devices that we showed off at the keynote, it is one project. We can literally go through and switch between all the build targets, build out, and then that's all we have to do. And this was kind of achieved by now the fact that we've got, if you've used Lightweight before, if you've used Scriptable render pipelines, you'll know that we can add in the Scriptable render pipeline asset in the graphics settings. We've now added this ability to override this on a per quality level basis. And this is really useful because now you don't have to try and create a script or kind of create your own system to switch out these render pipeline assets depending on the platform or maybe the capability of the device that you're building to. So here we can see we've got a render pipeline asset high. And if we go down to medium, we've got a medium one, low, etc. And this is just where shaders are recompiling. This is where we can turn off certain things. So for example, the low quality setting doesn't have shadow cascades. There's a lot of extra objects that we're rendering, and we get blurrier shadows, but it's fine, especially if it's on a mobile device. You've got a small screen, you're not going to notice this difference. And then we can go up cascades or shadow-like resolution up throughout these. If these aren't assigned here, then obviously it'll just fall back to the one that's set in the graphics settings. But it's a super nice, convenient way to handle quality levels and scaling across these platforms. As you can see here, I don't even allow high to be used on mobile devices. It actually gets stripped out. And then things like WebGL only has low, and it's set for that. Okay, so let's have a look at some shader graph shaders, because I love the tool. I didn't know how to write a shader before I joined Unity, which was just over 2 years ago. I had to learn very quickly, being on the graphics team. It turns out you need to know a lot about shaders, and there's a lot to know about shaders. So I quickly learned it. But to be fair, when shader graph came in, I was like, wow, it's just easier, especially if you want to do just some quick experimental stuff. You want to try out some ideas before even committing to code. It's just a nice, easy way to get there. And the shader code that shader graph produces is actually really quite nice. So, for example, I'm going to show you one of the shaders that I made, which is called, a cliff shader. Essentially, it's used on all the cliffs in the level. The first iteration of this, all the texture maps and etc. were baked down just out of Substance Painter. So these were using the normal lit shader in Universal, and I painted grass on top of the cliffs. The cliffs came kind of rocky on the sides, and down where they entered the water, I got darker and a bit more glossy. So this it looked okay, but I wanted to reuse rocks over and over again. I don't want to have, a ton of unique textures for each rock depending on where it was. So being able to utilize shader graph for something like this made a lot of sense. So at this point, I can take that information in shader graph. I can take the object's position, the height, the normals, etc., and build these shaders that react to the environment around it, which means you kind of get this semi-procedural kind of world building, which is great. So, for example, if we move this cliff down, we can see there's kind of a darkening gradient around the bottom of it, where it is also getting quite glossy. So if we move in here, get a good angle, we can see it is quite shiny at the base of it. And this is also the same for the grass. So the grass starts happening at a certain level, and it also fades off depending on the angle. So now we can rotate, and the grass will stick on top, and on the sides, the rocks will come in. So no longer did I have to worry about keeping all my rocks that I had hard-coded, painted down textures, at the positions they're painted for. So now I could, if I like the top of a rock and I wanted that just poking out of the ocean somewhere, I could do it, and it would look like it's meant to be there. So we have a look at this shader. I'll let it compile. Now it's fairly large, but I have a little bit of a step through of it. So the great thing about shader graph is now we've got the ability to group up things. And, you know, this did not look this neat not long ago. It was a giant mess, and I was like, well, I've got to show this to a ton of people, and they've got to make sense of it. I'm used to making noodles and, you know, a big spaghetti mess, but to be able to explain or show off something, you really want to be able to use groups. And it also helps if you're in a big team, being able to share shaders around and people can understand what's actually going on. So it makes use of some normal things, such as, you know, the grass coming in. And grass comes in with the vectors of the normals, and we can blend that in. So this is just grabbing the grass, the normal, and tiling it across the object. Down here, we then have the actual mask between the rock and the grass. We go back here, we can see it's the position of it, so it's using the position here to essentially get whereabouts it is height-wise. And this can give us the mask for, you know, if a rock's way down close to the waterline, it's not going to have grass growing on it. But if it gets up high enough in the mountains, it'll get some grass appearing. Same here with the wetness. It's also using another position to add that, you know, higher level of gloss around the base. And then we do things like, actually, I create the rock smoothness. There is no smoothness map as such. So the input map is actually, if we head back here, for the albedo texture, I get the color for it, but I'm also using the alpha channel to store some cavity maps. So this is starting to think about terms of like something like Substance Designer, right, or Substance Painter. We have got these kind of mask-generated kind of maps. So this was just pumped straight out of Substance as a cavity map, and then I can bring it into Shader Graph and actually create, you know, shading properties based off this cavity map using, you know, math, remapping, all that kind of stuff. And it means you can create this kind of reusable procedural shader system, which is really convenient. And I mean, this is the same shader that's running on the mobile device. There's no difference from the phone version to the console version. It's performant enough that we can just use it everywhere. So if we go back, have a look at another shader, which is a bit more complex and using some more of the kind of key features of Shader Graph. If we go to the vegetation, so here we got some palm trees. Ooh. Let's select that again. And can see we've got kind of like a subsurface effect. Now this isn't a subsurface shader that's with Universal, this is just a shader graph shader. And we can achieve stuff like this now with things like the custom function node, which lets us be able to use some HLSL inside shader graph. There's some other abilities that we can do here. It's going to be hard to see, but essentially there is, if we drop down to low quality setting, we should see the LODs take over. Oop, nope. Let's crank this way down. Okay, now we can see my lovely billboards that I made. They're not that great. But essentially, we can make use of the LOD information coming from the LOD component on the game object. And we can make use of this and switch out between our high-res mesh and our low-res billboard. So let's open up this. So this graph looks a little simpler in terms of the amount of nodes, but that's because of two things. One, it's using custom function node, so it's doing some code calculations within a single node. And the other thing is it makes heavy use of what we call subgraphs. So subgraphs are essentially a graph within the shader graph, and these can keep going deeper and deeper. So for starters, the trees themselves have a bit of sway with the wind. The leaves float around, the tree itself bends. And this is all entirely encapsulated in a subgraph. The cool thing about this is that we can reuse it in another shader graph if we wanted. If we wanted to create another variation of the vegetation shader, we can just straight pull, drag, and drop in this vegetation deformation. And if we go into this, we'll then load up the subgraph there. Full screen, so it's not going to work. And here we have essentially the node network that is deforming these vertex positions. And we've got essentially, it's similar to a shader graph shader itself. It has properties, and these properties are seen as the inputs to the subgraph node that you get. And the outputs are on an output node. And here you can also add as many as you want. They're different types, name them, etc., and they'll appear back up on the subgraph. Here, we've actually got, this is essentially taking vertex positions, it's figuring out the origin, it's doing some sine waves to bend essentially the vertex positions based off a few vertex colors. So the vertex colors are used as masks. This is essentially a copy of the technique that was used in Crisis for the vegetation there. And there's a really good write-up on GPU gems. But we can see here, there's a custom function. And there's also this. This is a smooth triangle wave. This is another subgraph. So we can open up this, and we go yet another layer deeper into this graph. And this is a bit more simpler, but we've got some nodes. They just come in. They're doing some calculations on the vector individual vector components of this. Now this could all be done probably in a custom function node. The custom function node could contain the entire HLSL information for the vegetation deformation, but it is really nice also being able to do it in a node-based system. It's very artist-friendly. You can look at it, and if you're used to node-based stuff, it's a very nice way to work. And the code that it generates is going to be pretty much similar performance-wise to the code that you'd write anyway. And again, I won't go into this, but this is another subgraph as well, this moves curve. So now if we go back up to vegetation, I'll show you a bit about the custom function node. So here we have an subsurface scattering kind of group that I've made. And the main reason this uses the custom function node is for getting the light information that's in universal render pipeline. So here I've just got a group, it's called main light. This is currently the code I've put in only makes this vegetation shader work with a one main directional light. I haven't put in the looping code to handle multiple lights. But here we need the world position of the actual object, so we're getting that in. And then this custom function node is actually looking at an external HLSL file called custom lighting. Here we also have a name. So this is the name of the function that it will look for in that custom lighting function HLSL file. So it's looking for a function in there called main light. Here are the outputs that that function has, and also the input. So the only input is the world position, but then it outputs the direction, the color, some of the attenuation of this light. So I'll just load up and show you what this custom lighting function node looks like. So we have two methods in here. I've added a second one. This is for use actually in the cloud shader that I've got. And it's just to get the ambient lighting. So this is quite handy, and I can quickly show that later as well. But the one we're talking about now is the main light. So you'll notice that in the name of the actual custom function node that I only had main light. I didn't have main light underscore half. And this is how Shader Graph can do precision based on the nodes. So Shader Graph now supports either float precision or half precision, depending on whether you need that extra information. This is especially important when you're looking at mobile devices. You want to be doing halves wherever you can if you don't need the extra precision values. Here is a little bit of code for the shader graph preview, because the shader graph preview itself isn't using the render pipelines. It's using the built-in renderer to render the preview node. So it has no knowledge of the actual lighting that's in Universal RP. So this is why when we're talking about the preview, we're just giving it some preset values that are, just safe values. We know it's going to handle these. And then we have essentially what is a snippet out of Universal RP's lighting loop. So in Universal RP, there's a lighting.hlsl file. It has tons of functions essentially about getting lights and getting the information back. This is a very similar kind of snippet out of that goes through, gets our light, gets our main light position, color, and etc. Based off where our objects are, where their vertices are. And then we are setting all of our outputs, which are defined here up in the actual function as outs, and then we're good to go. So this feeds back into our shader graph shader as variables that we can then just hook up to anything. So now we're getting the direction of the light, we're getting the color of the light, and with these things we can do our dot product to get our lighting shading on our normal surface, and then there's just some math and multiplications and some coloring from the albedo, etc. I also do some masking based on whether it's a leaf or a trunk. And this is a nice way how you can kind of extend a lot of shader types in Universal RP without having to write a completely custom shader from scratch. If you just need some lighting information, you want to do a subsurface, you want to do translucency, maybe you want to do clear coat, that's another thing. You can just bring in some code just to give you the information that you might not be able to find as a preset node ready to go. One last thing I want to show in here is the keywords. So shader keywords are essentially they essentially duplicate your shader. So they make it have multiple versions that have a certain part of code maybe turned on or turned off. So for example, in here, I have a keyword to control the vertex animation. So once the shader gets compiled, there'll be a version of it without the vertex animation included, and there'll be a version of it with the vertex animation included. Now this makes it so we can have quite efficient shaders. If I don't need the tree itself to be reacting to the wind, I can turn that off, and it skips all of that shaded code. If I didn't use a keyword and I just did a branch in the shader, so I did a switch between them, it's going to have to look at that when it goes to render this object. It's going to have to check, I'm doing both of these. It's more pressure at the time of rendering. Whereas here we can upfront go, here's two different versions of the shader. We're only going to use the one that we want at the time. These can just be easily added through the shader graph inspector, the blackboard. And there are two types. There's a Boolean and there's an enum. The Boolean is essentially, it gives you a tick box of on and off. It's a keyword that's on or off. An enum will give you a list, and then you can add multiple entries to the list. So say, for example, you might want to do a debug, like a drop down for your shader, and you have multiple things you might want to debug out. You can then have this as a switch. As you see here, it comes in, this is the vertex animation one, this is the Boolean type one. It comes in as an on and an off. You can feed in what comes in if it's off. You can feed in what happens if it's on, and then you get the output at the end of it. So that was a bit about the shader graph. Now I want to jump over to the camera callback stuff. So to do the planar reflections in the spoke demo, essentially we wanted to check before any camera renders, whether it's the game view here or the scene view, we want to go, okay, no, we need to render another camera. We need to render a camera that's flipped, and we need to save that out to a texture that then we can use later on the water shader. So if we have a look at the planar reflection script in this project, which is stored in a package, still funnily called Lightweight Render Pipeline Water System, we will see that the callbacks themselves are quite easy to use. So first off, here we subscribe to it. So on Enable, you'll want to grab the Render Pipeline Manager, and here we're looking at Begin Camera Rendering. Now this will get called every time a camera in Universal Render Pipeline starts its rendering, every single individual camera. There's a few here we can choose from. We have Begin Camera Rendering, which was what we're using. Begin Frame Rendering, which happens before any of the cameras have started, setting themselves up, and it will actually give you a list of all the cameras that are going to be rendered for that frame. The Begin Camera Rendering will give you the reference to the camera that's currently rendering, and then we've got End Camera and End Frame as well. So here I'm just assigning this Execute Planar Reflections method that I've got. And if we move down, one thing we also got to remember is to obviously deallocate from it. But if we come down to our Planar Reflections method, down here, so Execute Planar Reflections, and this takes two, let's just get rid of this because it's a bit. So we've got a scriptable render context, which is provided from the render pipeline itself. This is essentially like a container of information that the renderer is holding on to, stuff like the camera, the actual culling, etc. And then we get the camera that is currently rendering or executing this callback. So in here, I just simply go, well, is it a reflection camera or is it a preview camera? If so, I'm not worried about it. I don't want to do planar reflections for either of those camera types. And then it does all my code in here, which is setting up an upside down reflected camera, creating the render texture itself if it isn't already been created, and heading off a render in Universal Render Pipeline. Previously, this was done with camera.render, but in Universal Render Pipeline, to make it really nice and easy, and to make sure we avoid things like nested infinite loops of re-rendering, we have this Universal Render Pipeline render single camera. And what this lets you do is essentially it renders a single shot with the renderer that's currently applied to the given camera. So here I'm just going, I want to render a single camera, I provide my reflection camera that I've just set up, and it's going to render into this render texture because I've assigned it as the target texture here. And this can be useful for all sorts of things, depending on whether you want to just run some code at the beginning of a frame, beginning of a camera, or the end. So now we want to jump over to essentially the render features. So the scriptable render features or the scriptable render pass. Two of them were created for this demo. If we compile that script, maybe I broke something severe. I'm going to go with I probably did break something. So let's just get rid of that again. Start again. So if any of you here were for the talk earlier about Universal Render Pipeline and the general overview of it all, you would have learned a bit about how the rendering architecture kind of works. And the idea is that Universal has these scriptable renderers that you can plug in and plug out. The forward renderer that we supply is currently one of them. The 2D renderer is also one. We will be providing a deferred renderer. And you can make your own. In Boat demo project, we don't actually create a new renderer. We're just using the default forward renderer. But we have created a few scriptable render passes and scriptable render features. And these are most notable the caustics, which we have here under the water. And then also the water effects where you can see the trails behind the boats. So first I'll talk a little bit about the caustics one. And if we go to our renderer, we can see our list of renderer features up here. We have both a caustics renderer feature and a water effects renderer feature. Now the caustics one's pretty straightforward. It's got a caustics material, which is just a shader that does, I'll explain it a little bit, and a mesh that then it renders. So it's similar to the render objects render feature that is included in here in the Universal Render Pipeline. But the difference here is that I know I'm only going to render one object. I only need to render that object exactly a certain way. So I wanted a nice lean render feature that just did this. So I also added a debug, so we can look at exactly what it's doing. And essentially here you can see a plane, a giant plane that's getting scaled up quite large. It follows the camera. It's got this caustics material assigned to it. And what it does is it takes the depth texture that's currently been rendered by the universal render pipeline, converts it to world space coordinates, and then uses those coordinates as UVs for this caustics texture that then gets, tiled across in a bit of a UV noise to make the wobbling. And this is quite nice because here, if I look at any of these render pipeline assets, I've got two renderers assigned. One's the boat demo renderer, which has the water effects and the caustics, and one's the planar reflection renderer. The planar reflection renderer doesn't need to do caustics. It doesn't need to do the water effects because it doesn't see the water. It's rendering underneath the water and is used purely for the reflections. So why waste rendering time with this extra feature when we only need to have it for the boat, for essentially the main camera. So this is again making use of the fact that we can have a default one here, which will always use the caustics and the water effects. And then when I create the planar reflection camera, I tell it to use the second renderer that's listed in the pipeline asset. If we now look at the water effects is it's hit after rendering the opaques, and this is essentially a off-screen texture. So it's rendering to a render texture. It's used to control foam and the offsets. So I did attempt to add a debug, but I failed miserably, and it just turns off post-processing essentially. So let's go to the frame debugger and actually show you what's going on there. So if we go into gameplay, make sure we get to a part where we can see some trails from the boat. Probably going to have to turn off the center machine camera again. All my laptops are really hating me today, and it's locked up again. Oh, it's come to life. Okay, so let's just turn off this temporary cam. And yeah, that'll do. Okay, so now if we go down to the frame debugger, so we can see essentially the makeup of this frame, we enable it. I'm just going to collapse down these. In here, I don't know if you can see it. Okay, it's a bit small, but so we have all the essentially scriptable render passes that are getting executed. And we have things like first off, we're rendering our planar reflection camera actually. Currently, my render pipeline assets aren't in debug mode, but if I was to have it in debug mode, you would see multiple camera events essentially. So we'd see the planar reflection camera event getting called as its own standalone group, and then the main camera. The reason we have this in a debug mode on the render pipeline asset is because getting those pointers and getting the names of the cameras cause garbage collection, and we don't want that in your final game. So it's only in the debug mode. It's there for essentially if you want to see what's actually rendering and going on while you're making these systems. So here we're rendering the planar reflections, and then we go on to rendering our normal camera. So we need our shadows, we get our shadow map, and now we go into our water effects. So here we're setting up essentially a clear color of, these were the values that I needed for the map that I was creating. So this texture was used for doing normals and for doing foam, as well as the water displacement. So that's why it ends up being this cyan. But I'll show you what it fills it in with. So this is essentially what the boats are rendering in. This is some custom shaders that have a certain shader pass in it called water effects. And the custom renderer feature that I created essentially looks for any shader passes that have water effects in the name. And it only renders those shaders. So these are getting rendered all the time. They're essentially trail renderers that are attached to the boats and particle renderer that's attached to the boat. And these are getting picked up by this renderer feature only. They're not seen by the normal rendering. So this is creating, here we can see all of the passes it's creating. But this red channel is used for the foam. The green and blue channels are the normal channels. that I can then reuse to create the offsets in the water shader. And then the alpha is actually the displacement. So that's why we're at a mid-gray, so that we can go up and we can go down. And anything can get rendered into this. So you can create a particle that's shaped like a wave, and we can have that near the shoreline, and it will create a wave information that will then get rendered and used in the water shader to create foam and displacement. And that, I think, about wraps up everything in here. Essentially, yeah, the code itself is quite straightforward. I'll quickly show you some of that just to explain. We'll say with the water caustics, for example. So if we open up the water caustics feature, we have essentially our scriptable render feature here. And this is, again, our data container. This is where it holds our water caustic settings, which is our material, our mesh, and our debug tick box. Here's a little note, is if you do make essentially a class that holds your settings, and then you make a public variable called settings, the renderer feature list will automatically display these settings there without you having to create a custom editor. And in here, there's some settings for the debug, because it's changing essentially the blending of the shader so that we can see it in debug mode, and it goes back to the correct blending if we're not in debug mode. We add our render pass, and then here is our scriptable render pass, which is our render water caustics. And this is so we can see it in the frame debugger and see it where it's getting injected in the name of it. Here we've got a quick null out. If we don't have a material, then we just exit out. We don't want to try and render anything. And from our rendering data that gets passed to us in the execute method of our render pass, we can get the current camera's position, which is going to help us keep where the caustics plane is following the camera. We make a matrix for feeding into our mesh that then we draw here with the caustics material. And then we can just execute that command buffer and release it as well afterwards. And this is essentially a custom way of rendering a mesh itself. You can use this to do draw mesh instanced. You can do it to draw a full screen quad and do like a blit style shader. If you have a look at our universal rendering examples GitHub repo, which we had in a previous talk today, there's some much more full-out examples in there of how to set up your own scriptable render features. So I'd like to thank you all, and we have a bit of time for questions if anyone has any, but yeah.